Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video we will speak about polynomial regression models. You will learn about the general form of a linear model. You will see how to add flexibility by using polynomials, and you will understand that more flexibility is not necessarily better. If you think about the definition of the linear model, then you will know that the linear model is just a combination of features. And you can ask yourselves if that isn't perhaps too inflexible. So we have an example here. Y on the y-axis does not seem to be a linear function of x on the x-axis. It's like more or less this nonlinear shape. And if we plot y against x to the power of 3, so against the cubic polynomial, then we see that the relation between y and x to the power of 3 looks pretty linear. And of course we can think about other transformations as well, like the sinus function, the maximum function, the square root, or whatever. So it turns out that we can use linear models much more flexibly than we used to do, and it's still a linear model, and we'll see in a second why it's still a linear model. So perhaps the interpretation might be less straightforward, but we will come to that later. Recall the previous definition of a linear model. We have a function f that is theta 0, some intercept, plus a sum of weighted feature values, so sum of theta j times xj, and we can write it that way too. And in fact, this is just a special case of the true linear model, if you want to say so. So the true linear model is this here. The function of x is still intercept plus, and then a sum of weighted basis functions phi j. So we call the functions phi basis functions, and we can still compute weighted sums of those basis functions. So with theta 0 plus theta 1 times phi 1 of x1 plus and so on, and each feature xj can have a different basis function or transformation phi j. So if we want to get from the general case to the special case of equation 1, then we just choose the identity for each phi j. Okay, so the identity function is just, would just be fj of x is just exactly the same thing as x. Okay, and sometimes when we speak of the linear model, we just imply that all those functions are identity functions. So now the question is a model like this, theta 0 plus theta 1 times x squared, really a linear model? And of course, it's not a linear model in the covariates. So let's have a look at these formulas here. For a model to be linear, it has to hold that a times f of theta plus b times f, a times f of x plus b of times f of x star is the same as if we take the weighted sum here inside the function. And we can now see that this is not the case. So let's go through this step by step. So the first thing, or the first part of the weighted sum, would be a times theta 0 plus a times theta 1 x squared. Okay. And the second part would be b times theta 0 plus b times theta 1 x star squared. Okay, and now if we rearrange terms such that the ones that correspond to theta 0 go together and the others corresponding to theta 1 go together, then we have this equation here. So that's kind of the left-hand side of the equation. And if we go over this from the other side, so we start here and plug in ax plus bx star in that function here, then we directly get theta 0 plus theta 1 times, okay, just the argument of the function squared. And well, this is clearly not the same as the left-hand side of the equation. I hope that's clear. It's like already clear here that theta 0 is not the same thing as theta 0 times a plus b, and of course it holds for the other part as well. But if we think in the parameters, we can see that that this model is linear in the parameters, which means that if we do not alter the first argument of the function here, but the second argument of the function, theta and theta star, and then we just plug in the definition above, then we have, okay, let's clear that. Then we have a times theta 0 plus a times theta 1 x squared plus, and then the second part is b times theta 0 star plus b times theta 1 star x squared. And we can rearrange the terms to this second formulation here. And this is clearly the same thing as directly plugging in a theta plus b theta star here inside the function. So this means the model is linear in the parameters, but it's not linear in the covariance. And you can also see a small example here on the right-hand side, and this plot in this case with linear functions. So these are just plain lines in that plot. If you add up the blue line and the yellow line, then you end up in the above line here. And you can just do this by adding up the intercepts. So 0.5 plus 1 is 1.5, and 0.4 plus 0.8 is 1.2. Okay. And then in the end, we can still speak about the design matrix X, which incorporates all the possible transformations. So we have still a design matrix where the first column is the intercept column, and then all the other columns are just the transformations of the feature values. So we no longer have here in the first row 1 and x, 1, 1, and x, 2, 1, and so on, but we have 1 and phi 1 of x1, 1, and phi 2 of x2, 1, and so on. Okay? And in the rows, there are still the observations. And then, since we have this design matrix, we can use normal equations as usual to solve this optimization problem or to estimate the parameters. Okay. So now you know about the general version of the linear model. Now we can go a step back, let's say, and have a more special version, which is still more general than the linear model you might have known beforehand. So we will speak about polynomial regression. This means that for those functions phi, we don't use just any function there is, but we use polynomials. Okay? So a polynomial is just a sum, a weighted sum of the monomials. So we have beta k times x to the power of k, and we sum over all different possible monomials up to order d, and d of course is a natural number. Here on the left hand side you see a plot of y and x and you have the different degrees of monomials here, and on the right hand side you also see again exactly those monomials, but you also see some data points and a weighted sum of those monomials, and this weighted sum is already with the estimated parameters. Okay, so the blue line here, that one, yeah, it's that one, is the weighted sum. So that's directly f d of x in that case. Okay, so you take those monomials, you weight each monomial, and then you sum the weighted monomials. And now the question remains how to estimate those coefficients here. Because what we have now, okay, let's clean a bit first. What we have now is a function theta 0 plus theta 1 phi d of x. But this phi has now additional parameters, which means we have theta 0, we have theta 1, and then we have beta 1 to beta d. Okay, so what happens now? We can write this down as follows. We have still theta 0, okay, that remains untouched, plus the sum of theta 1 k times x to the power of k. Okay, please note that now theta, as opposed to in the left-hand side, has a subscript 1 comma k, which says that this is the weight for exactly that monomial, but it's not the same thing as the beta k above. So we could say that theta 1 k is the same as theta 1 times beta k. Okay, so then these are the same and those are the same, and well, we have rewritten this and this means that we have now in total, if we just try to estimate theta 0 and all those theta 1k, then we have d theta 1k's, okay, and 1 theta 0. So in total we have d plus 1 parameters which we want to estimate. And this means that we can again set up this design matrix here. We have an intercept column for theta 0 and then all those other columns for those monomials, and then we can just estimate those parameters. Let's have a look at some examples here. In the upper part, univariate regression. The data generating process is like this. So we have 0.5 times the sinus of x plus a random Gaussian noise with mean 0 and standard deviation 0.3. Okay, those are the black points here on the left-hand side. And then we have two models. The first model is a linear model with degree 1. So d goes just to 1. And the second model is polynomial regression with degree d equals 5. So the black line here is the polynomial regression. The yellow line is the linear regression. And we see that, of course, there's a difference. We don't, well, perhaps we know which one is better. I guess degree 5 is better, but we would have to test this on untouched test data, of course. But, well, visually we can already see that it's better to use a polynomial of degree 5. What we don't really know is if perhaps a polynomial of degree 3 or 7 or 9 would be better. So we will come back to that problem in a different chapter. But for now, perhaps just memorize that there is a difference and that we have more flexibility with those polynomials. And then in the lower part, we have a bivariate regression. So we have two features, x1 and x2. And here we have the target y. The data generating process is 1 plus 2x1 plus x2 to the power of 3 plus, again, an additional random Gaussian noise. And we have a model with d equals 7. Okay, so we don't have two different polynomials here to not complicate it too much. But you can see that this surface here, this blue thing here on the left-hand side, fits the data pretty well, I guess. Okay, higher D allows to learn more complex functions. So we have a richer hypothesis space, or we could also say we have a higher capacity. So if we have degree 1, then it's really just this linear line here. And with higher degree D, we have, well, more flexibility, and the functions get more flexible, more wiggly. So we could say, okay, higher capacity is great, rich hypothesis space, this sounds great. Why don't we just let go D to infinity? So that's a bad idea, because the data contains random noise, okay, which is not part of the true data generating process. And if we conceive a model that has a too high capacity, then this learns all those spurious patterns. So it doesn't generalize to new data. And what we try always with machine learning is to learn a model which is not only good on the training data at hand, but we want to transfer this model to the future. Okay, we want to predict with this model, we want to generalize to other data sets, to data sets which lie in the future or which lie in different parts of the world or whatever. So we want to generalize, and with just interpolating points with a very flexible polynomial, which is of course possible, we don't really achieve this goal. Also, a higher D can lead to oscillation, especially at the bounds, which is called Runge's phenomenon as well, but we will not speak about this in detail here. Let's have a look at a concluding example at the OpenML task Daily Bike, which tries to predict, or where we try to predict a number of rentals, and the features are some weather conditions, so it's about bike rentals. And we do a non-linear effect of temperature. So we have this polynomial of degree D, which we can adjust, of course, of temperature, and season is a categorical parameter. A polynomial doesn't make any sense here. And humidity is a continuous parameter, so we could use a polynomial here as well, but we don't do it in this example here. So what you see here on the left-hand side is the test error for test and training data. Of course, it's worse for test data. But the point is that we want to find a sweet spot where the test error is minimal. So we'll speak about this in depth in the evaluation chapter. Here we did some tenfold cross-validation, which you can just accept for now. And the point where the error, so in that case the root mean squared error is minimal, is with degree D equals 3. So I would say that's the best value of D, which is then a hyperparameter of this polynomial regression. And you can see on the right-hand side the two estimated functions of temperature to predict rentals. And from the data points, to be honest, I wouldn't really be able to judge if D equals 1 or D equals 3 is better, because there are just so many points. And apparently there's quite some noise in these data sets, so we don't really know too sure about that. But of course, we can still just trust those test evaluations, because we did those this tenfold cross-validation and saw that the test error is minimal for D equals 3. Okay, so here there's a small table of some results where you also see that the test error for D equals 3 is smaller than for D equals 1. You also have the estimated parameters, intercept, the linear part of the function, and for the polynomial also the quadratic anticubic part, and well, then the estimators for this categorical feature, season, and then for the continuous feature, humidity. So the conclusion here is that flexible effects can improve the performance of a model. And the caveat is that, of course, we have to be careful not to overfit so not to be too flexibly, because then we wouldn't generalize too well on new test data.